come back to our third and final segment, we're still talking the mole. Okay, so the idea of a mole is that it has to do with the amount of matter. So we're saying a mole of any substance has got that constant number of particles, and this is actually the Avogadro number, right? So that's our Avogadro number, okay? So this number is constant, it doesn't change, okay? So this is the number of particles. Whatever particles can be, it can be atoms, right? It can be molecules, it can be ions, it can be anything, okay? But the number is constant. So in an element, the particles are atoms or molecules, if it's a molecule of an element. In a compound, the particles are molecules or formula units. These are ionic compounds, or it could be ions, right? Okay, so how moles relate to number? So we are saying that if we are given the number of particles and we want to determine how many moles, we must know that for every mole there is an Avogadro number of particles. So this is kind of straightforward to say that the number or the moles present in a sample depends on the number of particles versus the number per mole, which is the Avogadro number. So this is our constant 6,02 times 10 exponent 23 per mole, right? So in this case, we've got number of particles, and then this is the number of particles, okay? So that's our number of particles, okay? Say, for argument's sake, we are talking about a dozen, you know, for us to say how many dozen, we say how many, you know, units are there, and then we divide by 12. In this case, we divide by the Avogadro number, which represents the number of particles per mole of any substance, okay? And then let's look at, shift our attention a little bit and look at gases and see how it relates to gaseous substance in terms of quantity of matter, okay? So a sample of an element or compound in a gas phase has a fixed mass. So we always talk about a fixed mass of a gas. So this phrase will be very common, fixed mass of a gas, right? But we know that gas particles, they move very fast, they've got high kinetic energy, they fill all the spaces, but what doesn't change is the mass. So if we say the mass is fixed, we are saying that it's constant, okay? So the amount of matter that makes up a gaseous substance is the same. It is constant, which is the mass. So the volume of the sample can change depending on the temperature and pressure. This takes us to something very important to say that, you know, the pressure of a gas depends on how fast the particles are moving, you know, and how frequently they collide with each other, as well as with the walls of the container, which contributes to what we would know as the pressure of a gaseous substance. So that would depend on the temperature, okay? Right. But where are we going with this? We talk of standard conditions of temperature and pressure. So standard temperature is 0 degrees. This is Celsius. This is set at 0. So when we talk about a standard temperature, we're talking about a temperature of 0 degrees Celsius, right? Now, standard pressure, 101.3 kilopascals, which is also equal to an atmosphere, which is 1 atmosphere, right? So this is STP. So at a particular for a particular gas at a standard temperature and pressure, the volume of a gas will be a certain amount, because the volume depends on temperature as well as pressure, right? Okay, so Avogadro law, what does it say to us? It says that any sample of an element or compound in a gaseous phase, but remember, this is about gases, with the same volume at the same temperature and pressure will contain exactly the same number of particles. So what are we saying here? At standard temperature and pressure, the volume occupied by any gas or a mole of any gas will be constant. That we call the molar gas volume. So what is a molar gas volume? It is the constant volume occupied by 1 mole of any gaseous substance at standard temperature and pressure. And if we talk about a mole of a gaseous substance, how many particles make up that gaseous substance is the Avogadro number, which is the 6,02 times 10 exponent 23 per mole, right? So at STP, which is at standard temperature and pressure, 1 mole of a gas occupies 22,4 cubic decimeters. So that's the volume. So VM stands for molar volume or molar gas volume, right? Okay, how moles relate to number? So at STP, 1 mole of oxygen gas occupies that volume. But now, let's agree that if we talk about a mole of oxygen gas, it has got a fixed mass. So this mole contains 6,02 times 10 exponent 23 molecules, okay, of oxygen. Okay, so that's the number of molecules present in 1 mole. So what's the volume that it will occupy? But to qualify this, it must be at standard temperature and pressure. That volume is 22,4. Hence, we are saying the molar volume at STP, it's actually the volume occupied per mole. So this stands for per mole or 1 mole, all right? So a mole of any gas at STP occupies a constant volume. That's the main point, right? Okay, so given a sample of gas at STP, which is the volume, knowing that each mole occupies a constant volume, then it takes us to this equation which says moles of a gas is equals to volume divided by the molar volume. So this molar volume is 22,4 cubic decimeters per mole, okay? While this is the volume of gas, okay? This is volume of gas in cubic decimeters, right? So this will be in cubic decimeters. That's why the cubic decimeters for the volume divided by the cubic decimeters per mole, okay? These will cancel each other. We're left with over per mole, which will give us the mole, okay? This is actually in moles, okay? Right. So that's the main idea, okay? All right. Having said that, let's look at practical examples. How do we calculate the molar mass of a substance? How do we know? First of all, we need to identify the fact that in the first question, oxygen gas, we need to understand what is the formula of this substance, O2. It's a diatomic element, okay, which exists as a molecule. And each one of them has a mass of 16. So if we want the molar mass of oxygen, okay, it's equals to 2 multiplied by 16, because each one of them is 16. Then this would give us 32 grams per mole. Okay, that's the molar mass. What about water? Molar mass of water, okay, is equals to, the formula suggests that there are 2 atoms of hydrogen for every oxygen atom. Okay, then this tells us that it's 2 multiplied by 1, because there are 2 hydrogen, plus 16, okay, which gives us what? 18 grams per mole. Okay, so that's the molar mass of that those 2 substances. Okay, so we've done that. Okay, now the question says how many moles of oxygen are present in a sample that has 22,4 grams. Now we want the moles, okay, which is the quantity, right? And we know that each mole has got 6,02 times 10 exponent 23. So if we are looking for the number of moles, or the moles rather, okay, we are saying that moles, and sometimes we say number of moles, but actually this represents the moles, okay, which is a number after all. It's mass of sample divided by molar mass, okay? Now, do we have the mass of the sample? Yes, it's 2,4 grams, all right? Even if we don't put the units, we know that N is in moles, okay? Now, we have also calculated the molar mass of oxygen and found it to be, if we can go back quickly, the oxygen is 32 grams per mole, okay? So the molar mass of oxygen is 32 grams per mole. So this is divided by 32, okay? So whatever we get will be in moles, all right? Okay, so if we go to our calculator, this gives us 2,4 divided by 32, okay? Divided by 32, okay? That is a decimal fraction, 0,075, okay? 0,075, 0,075, Okay, so this is less than 1 mole because it's not 0.075. Okay, so this is the quantity of moles that is present in that sample, right? And then how many moles of oxygen are present in that 22.4 cubic decimeter? Okay, we want the number of moles, we're given the volume, all right. But here, what do we have? We've got the volume of oxygen that it occupies, but we know that a mole occupies what you call 22.4. So we know that N is equals to volume of sample divided by the molar gas volume, right? Okay, so the volume of sample that we're given here is 2.4, okay? Cubic decimeters. It's no longer the mass. Take note of that because that's the volume of the sample, okay? Divided by, we assume that this is at STP, okay? So if we assume that this is at standard temperature and pressure, we know each mole will occupy 22.4, right? So we are looking for the moles that are present, okay? So this works out to 2.4 divided by 22.4, right? So this gives us that number of moles, which is 0.12, right? Right, so this is equals to 0.12, all right? So N, which is the moles, 0.12 mole, all right? So this is the amount of moles that are present in that sample. So the idea is actually to work out the number of moles, but it depends what you're given. From the two equations, if you are given the mass, then we'll use the molar mass. But if you are given the volume and it's a gas at standard temperature and pressure, we can use the molar gas volume, okay? Either way, it gives us the number of moles, or the moles, actually to be precise. So the idea of quantifying matter is we arrive at a point that it's always about the mole. Okay, so and each mole contains the same number of particles. So that's the main idea. So in the big question of how many molecules of water, once we are given the mass of water, we are able to use the molar mass of water to determine how many moles. And then from there, if we have the moles, we'll multiply by the number of particles per mole to get the actual number of molecules in that sample of water. So that question, if you think of it, it's actually doable in the sense that now we understand that in terms of quantifying matter, everything is about the mole. Having said that, this brings us to the end of our session for today. From myself, Themba Ncube is cheers and bye-bye for now.